Hello everyone and welcome to another lecture. Today we will be talking about multivariable functions, and that is how we can define multivariable functions, how we can do some manipulations with it in Mathematica. We will be also looking at limits and differentiation of multivariable functions, and finally we will try to plot them. So a multivariable function is a function of several variables, and the way we can define this in Mathematica is similar to how we dealt with the single variable function. So let's say I want to declare a function called f, but now I want it to be a variable of x and y. So first type x, remember to give an underscore, and you put a comma to separate these x and y's, and then you put an underscore, then you define this function. Let's call it xy, that is x times y. Also put a space, or you can use the multiplication sign. For this example I'm using the space, and let's say x plus y, xy plus 2. This is our function. So let's run it. You can see that it has run successfully. Now I want to know whether Mathematica actually took it as a function of x and y. So to do that, let's try to give some arguments. Let's say x equals to 1 and y equals to 1, and we expect the answer to be 3, and let's run this code, and we're seeing this is answer 3. So this is right. Let's do another check. Let's give x equals to 0 and y equals to, let's say, 700, and the result is 2. So Mathematica took this multivariable function. So instead of xy, I could also write z, and let's say it's 2 plus z squared, z squared, like this. So we have to run it again, and now if I do this 1 1, you can notice that it's still giving me 3, but if I put another one over here, this is giving me 4. So you have to put all the arguments when you want to calculate a numerical value. That's the idea. So this is how you can define multivariable functions. And the next thing we want to see is that we are using these functions, and we want to see how the limits take place while we use Mathematica. So now we want to turn into the limits of this multivariable function. To do that, we first have to type limit, and then we need to call our function x comma y comma z, and we put a second brace, and inside this second brace we are going to write the limit, that is what we want as x approaches to some number, y approaches some number, and z approaches some number, and we want to separate them by commas. So let's say x approaches 0, y approaches 0, and z approaches, let's say, 1. Let's try to run it, and you can see that the answer is 3. So intuitively, since this is not a very complicated function, you can see that as x goes to 0, the part xy over here goes to 0, and when z and y is not in a single manner, that is, y is not isolated in this function. So as x goes to 0, this whole xy thing goes to 0, so then y goes to 0, and z goes to 1, right? So instead of z square, we'll have 1. 1 square is 1, so 2 plus 1 is 3. So this is just it. And now let's say we want to make our function a bit complicated. So I want to type sin x plus y plus z. Let's see what happens. We run it first, because Mathematica otherwise would take f to be xy plus 2 plus z square. So that's why we have to run it again, and then we can evaluate this cell, and as you can see, this is giving us the answer 2 plus CSC. This CSC means cosine. So this CSC so as you can see, Mathematica gave us a nice result. And if you want to have the numerical value, all you can do, you can either click here, or you can just take this n over here and put them inside these braces. If you evaluate it, there you go, that's your limit. So this is how you can declare any type of multivariable functions. In fact, you can add more variables if you want, but I'll just stick to 3 variables now. So the next thing that comes to our mind is that how we can differentiate, that is differentiation. So the idea is very simple. You just have to type the command D, and remember this is multivariable function, so again you have to call in the function first with commas separating the variables. Then what you need to do is you need to type x. Let's say you want to know the function and then you differentiate with respect to x first, then you want to differentiate with respect to y. That is, you want to know the cross term. Let's say d square f by del x del y. So for that, let's say I want to differentiate with respect to x first, so and just one time, so I'm typing 1 over here. I put another comma and then I type y, let's say 1, and if I do this, this is our cross term derivative. And to make sure that this is actually working, let's get rid of this sign so that this becomes a very familiar thing, and also the z squared. Notice that I haven't crossed z over here, so it doesn't matter. So if I do this again, this is just 1, right? Because first you take the derivative with respect to x, so you have this y plus 2, and then I'm sorry, not y plus 2, just y, because when you take the derivative with respect to x, the constant plus 2 just goes away, and then you take derivative with respect to y. So this is how this derivative thing can work, and it will work in a sequential manner. So you have to be careful, like which one you want to do first. So if you wanted to, let's say you add this z times x times y, and let's say I want to have z comma 2. You see that the second derivative for the z doesn't exist, so you can think or guess that it should give you a 0, right? Let's see. And yes, it is giving us a 0. So this is how you can differentiate. Oops, I made a mistake here. It should be, so sorry for the typo, I didn't notice, really apologize for that. So this is how you can differentiate for multivariable functions. And the next thing we are going to look at is how we can plot, that is plots. So to do that, Mathematica has a command called plot3d, and the reason we are using plot3d, and remember from now on we'll deal with function with 2 variables. Let's say I want to declare g of x underscore comma y underscore, and let's just define this function to be like this: sine xy plus sine h, that is sine hyperbolic x plus y. This is just some random function I'm taking. So let's run it first. It has run successfully, and the reason we will be using plot3d because for each and every x and y we will get a point, and then that is an output, that is g of xy, and we will plot that point as z, as our z coordinate. So what will happen is that we should get a surface in a 3D space. So let's try to see what happens if we do that. Let's say plot, you can see that option emerging, plot 3D. I'll choose that, and I want to type my functions, that is g of xy, and then I want to have my intervals. Let's say I want to have x from -5 to, let's say 7, and I want my y's to be -10 to +10. Let's see what this gives us. you can see it took a bit of time and it has generated a surface for us. And the nice thing about this graphics is that you can actually move it. You can make it bigger, I think. Yeah, you can make it bigger. Just select on it and stretch it. So you can see that this is a very nice surface, though it doesn't seem that interesting. And there something you will see like this, for example here, this solid lines. And what is happening here is that there is some numerical glitches, and because of that you might see sometimes when you try to plot a very complicated function. So Mathematica is trying its best, but it's having a hard time. And what if I divide this thing with x times y? Let's try to plot it again. So let's run this and then use this plot. And now you have a surface, but you will see some discontinuity. Notice this area, this white lines between these four fractions. This is happening because you see that at x and either x or y, when one of them is 0, there is a singularity of this g of xy function, and that's why there is no specific numerical value. So that's why you are seeing these discontinuities. But then again, this is a very nice graphics, and you can plot more interesting functions with it. Let's say instead of sine xy and sine hyperbolic xy, let's just take a cos function over here. Let's take cos, and instead of multiplication we do a plus, so that we don't run into those discontinuities. But then again, instead of xy, I mean from including this 0 in the interval, let's try to plot it for all the positive values. Let's say from 1 to 10, and this is from 2 to 8. Let's try to do that, and let's see what happens. So this is our graph again. So now let's try to look at another example of plotting. This time I'm going to call my function as, let's say, capital G, and I want to declare instead of xy, now I want to, let's say, write p and q. So p and q, I want to define them as, let's say, p times sine q plus q squared p cubed minus 6q. And let's try to run it first, and just to check whether Mathematica really understood what we said to him. So we can see that it's all okay. So now let's try to plot it. Oops. So let's plot 3D. We go for g of p comma q, then we specify some intervals. P, let's say, minus 5 to 5, q, let's say, minus 6 to 6. And now we want to add some attributes. That is, first of all, we want to label our axes. So axis label, this will be, first we have to do this p and q, and let's see what that gives us, so that we can see the output, and from there we can infer that whether we will be able to add more labels for axes or not. So this is my axis label, and let's say I want to change this color, because you can see that Mathematica always uses this default color, and let's try to choose a rainbow setting. So use color function, color, a color function, and let's call it rainbow. So we have written our code clearly, and let's run it. as you can see that we have made some errors, and the error lies in the fact that I haven't put a comma over here. So this is how you can read your errors and correct your code. Let's try to run it again. Is it running? Yes. And as you can see, Mathematica gives us a really nice graph and the color, and at the same time, if you just enlarge the picture a little bit, yeah, it took some time, and it's also showing you this P and Q's, right? So let's try to add another thing, that is my g of, let's say, x comma y, oops, xy. So if you do that, again this is running, as you can see from evaluation part. So this is your g of xy, this is p, this is q, and you have the plot. And finally, let us save this plot for a bit. And an important thing to note is that you can save these pictures. So you can just type save image as, or if you are using the offline version, you can also import it as PDF. So finally, I want to talk about a parametric plot. Let's say you have a particle moving through space, that is x, y, and z space, where I mean by x, y, z space, I mean the coordinates as x, y, and z, and these coordinates depend on some parameter, let's say t, that is time. So how do we plot that? Can we plot that in Mathematica? That is, I want to see the particle's trajectory in a 3D fashion. So can I do that? So let's think of a particle that is circling in the xy axis and going up in the z axis. Intuitively, this trajectory will look like a helix. So let's try to see whether Mathematica can give us or not. And to do that, we need to use a command called parametric plot. So type parametric plot 3D. You put your arguments over here, and if you just click on here, you can see that I have to put the functions in a list, that is the x component, f of x, f of y, f of z, and then this u is our parameter. So instead of u, we are going to use t. So if you do that, let's say since this is a circle on xy axis, so first you have to put this f of x, and let's say this is sine t, right? And y of x will be cosine t, and z of x will be just t. And then you have to specify the range. For example, t ranges from -2 to +10. If we do that, you can see that we have a graph like this, and though it's a bit stretchy because our parameter ranges from -2 to 10. What if we took t from, let's say, 0 to 10, and we want the particle to slow down a bit on the z-axis? So this means you have to reduce, you have to put such a number in front of t that is less than 1. So you have to divide, let's say, t divided by 20, and let's do that. You can see now we have a really nice feature. And now if you just increase the y value, let's say 2 times cosine theta, no, sorry, not, yeah, so let's just time 2 times cosine theta. Let's see what happens. So you can see that instead of circle, now it's like an ellipse, but it's going up, and I want to make this range a bit bigger to see what happens. You can see that this particle is just moving on the spiral, and now you can see that this line is blue, and it's kind of a thin line, right? So what we can do here is that we can use the command called plot style, and then we can type the color first, let's say red, and I want to add another attribute called thickness as 0.03. Let's see what happens now. Now I have a really thick lines, like really thick, and I want to stretch this. Since 0.03 is a bit thicker, let's try 0.01. So again, we can move the graph, we can make it bigger, and we can also label. That is, we want to do axis label, and let's do that. It's similar as before. So here, let's say X, and then we want to say Y, and comma, we want to type Z. If we do that, then we have our axis plotted, that is X, Y, and Z. So this is how you can use parametric plot to visualize some things. And now what we can do, a neat trick, that is, let's say this G of PQ is giving us some region, let's say this rainbow region, and we want to impose these two graphs together. That is, our particle is going through this region, so we want to put these two graphs on the top of each other. So to do that, we just type show, and let's say I am storing this parametric plot as, let's say, line plot. This is how I want to store it, and let's say this guy as surface plot. Close. So you have to run it again so that Mathematica understands that you are taking this plot on the surface plot variable. And let's just type this. You can just copy it over here so that you don't do any mistake. Just type this and put a comma over here. Take this line plot here, and let's wait and see what Mathematica does. As you can see on the right side, it's evaluating, and it has evaluated in fact, and look at that. So using these two commands, we can actually see our particle moving through this space. As you can see, this line is not that thick because we reduced the thickness, and let's say I want to increase the thickness, so just type 2. That will look a bit bad in this window. Okay, now it's, oh no, it looks good as well. So let's try 0.02. So you have to be careful, and sometimes you have to give a trial and error by regarding these attributes, whether which one works for you the best. And if you do that, you can see that this is our region of interest, and this is how you can use these parametric plots to your advantage. That is the type of thing you are dealing with. So this will be it for today.